Now let's move on from here and let's go into some more examples where we can at least start with second quantization. And in this video, I'll be talking about the total energy of non-interacting fermions, and we understand that fermions have spin half, and the particles like electrons and protons, they fall in the category of fermions using second quantization. Now, what is important here is basically that I would like to give the statement of this problem. What we have basically is we have a non-interacting gas, and this gas is made of fermions, and for the sake of argument, let's assume them to be electrons. Now, at absolute zero temperature, the particles obey uh, the particles the particles obey Fermi-Dirac statistics. The fermions obey Fermi-Dirac statistics, and obviously it follows the Pauli's exclusion principle, uh, uh, which states that no two fermions can occupy the same quantum state. And using second quantization, what we intend here is to calculate the total energy of this non-interacting gas, non-interacting rather Fermi gas at at t equal to 0. And assuming the system is confined to a volume equal to V. And the approach that we will adapt here is that we will use second quantization to set up the problem and calculate the total energy of the fermions by summing over the occupied states up to what we call as Fermi level. And the energy that this Fermi level possesses is called as Fermi energy. Now, fermions are antisymmetric, and they have anti-commutation relations for creation and annihilation operators. So and at the same time, we have to inculcate the Pauli's exclusion principle, because Pauli's exclusion principle ensures us Pauli exclusion principle. It simply explores us. It basically ensures that each quantum state can be occupied at the most by one fermion, one fermion. So this will be the approach, and now in second quantization, again, what we have is fermions are described by annihilation and creation operators, and if I take my annihilation operator as ck cap, and this is my annihilation operator, and ck cap dagger as creation operator. So if this is the case, we understand annihilation operator will remove a particle, and the creation operator will add a particle to the system. And there we have these anti-commutation relations like ck and ck dagger leads to chronicle delta, that's kk dash, and the rest like ck and then ck dash is equal to ck dagger, ck dash dagger is equal to 0. So these operators for fermions, they anti-commute with each other. So we have anti-commutation relations. Now the number of operators that let us introduce a number operator, as we have introduced in the previous videos as well, the number operator. Let me take that number operator as nk cap. For some specific state, say that's a k state. So in that case, I can define this number operator. I can define it as nk cap is ck dagger and ck. And its eigenvalues, if we talk about eigenvalues, will be either its eigenvalue will be equal to 1 or it will be equal to 0, reflecting reflecting the fact that's introduced by this Pauli exclusion principle. So again, I would like to say that fermion state can be either empty or it will be occupied by one fermion. Now, to write down the total number of fermions in the system, if I have to write down the total number of fermions, so what will be that? That will be n cap is the summation of k over ck dagger and ck. So if we move on from here, now what we want is we want the Hamiltonian. Okay, so we want the total energy of the fermions, and we have assumed that there is no interaction between these fermions, and we can write down its Hamiltonian now. So Hamiltonian can be written as sigma k epsilon k, then you have your ck dagger, and I have ck, where this ek, we know this ek is the energy, and it's the energy of the quantum state that's occupied, and this ek is h cross square k square by 2m. Now, this is the energy of the single particle state with the wave vector equal to, so wave vector with wave vector equal to k. Now, if I think about it at absolute zero, so at t equal to 0, what fermions will do, they will be available up to the quantum states, up to this Fermi energy, EF. Now, so what can I say? So the states that are below this Fermi energy level, at absolute zero, all of these levels are going to be occupied below this Fermi energy level, below this level, and the energy that's possessed by the highest state of this this range of levels is called as Fermi energy. And Fermi energy, it corresponds to this highest occupied energy level at t equal to 0. Thus, the total energy of the system is the sum of the energies of all occupied states that we have up to this Fermi energy level. Now, in order to find the total energy, because we want to find the total energy, energy, what we do, we first need this wave vector k, okay, and this wave vector will reflect as kf, and we call this as Fermi wave vector. Now this kf is Fermi wave vector, and this is what defines the boundary of the occupied states. It gives us the boundary of that occupied states in the momentum space. Now, the number of fermions, which is n, in the volume V, is related to this kf, Fermi wave vector. It is related, the three are related by density of states. Density of states. Number of energy levels per unit energy range. That's our density of states. And what's that? That is n is v is the volume by 2 pi whole cube, then integral magnitude of this k less than kf d3k. So this is our number of fermions at this temperature. Now we have to evaluate this integral, and we can first change this. We can first change this integral in spherical polar coordinates, and we can use as we use in momentum space. What we use is 4 pi p square dp. Now instead of p, we are going to use k here. So we can change this integral, and the limit of this integral will automatically be kf, because all the particles are distributed up to the highest level, and that highest level is our Fermi level. So here what we do is we write down this n, and we write down it as v by 2 pi whole cube, and for writing down 4 pi square, so integral, then we will have k square dk, and the limit of the integration will move from 0 to kf. That will be the case, and here we can do it now. This is v by 2 pi whole cube, then we have 4 pi square, and then we will have k to the power of 3 divide by 3 from 0 to kf, and we'll give the upper limit, and what we will come up with is you'll have cancellations. We'll have v by 2 pi square, so you can cut these numbers. Okay, this is cube and this is square, and you'll get v by 2 pi square here for k, because the upper limit is kf, it will become kf cube divide by 3. So this is our number. This is our number of particles being occupied in those quantum states up to kf. Now we can solve this equation for kf. Now solving for kf, what we will get is kf will come out to be, you'll take all that shit on the other side, and you will find 3 pi square n by v whole to the power of 1 by 3. All right, that should be the case. Okay, so because you can do it, all you have to do is to transform all the terms on the other side, and finally you will come up with this. Now the Fermi energy, what we have, this is our kf, and we can write down kf. What we have, E is h bar square k square by 2m, so I can replace it by h cross square kf square by 2m. So I can think of writing E as ef, h cross square by 2m times kf square. So the square of this is 3 pi square n by v whole raised power 2 by 3. So this will give me the total energy. And the total energy of the fermion gas is the sum of all the energies. And in second quantization, how do we write that? We write that as E total. Okay, so what will be that? That will be sigma, then you will have EK, you will have CK dagger, then you will have CK. Okay, and for the magnitude of K is less or equal to KF. Yeah. Now, if I talk about at T equal to 0, what's going to happen? The magnitude of this K is less or equal to KF, and you have all the states occupied. That means the number CK dagger and CK is equal to 1. So for the total energy, which is sigma ek, and where the magnitude of k is less or equal to kf, this will be simply v by 2 pi whole cube integral k less or equal to kf, and then you will have h cross square k square by 2m and dk. That will be the case. And in spherical coordinates now, again we will go for the same kind of procedure, and we will have 4 pi k square dk here, but so we will have k to the power of 4 here. So what I mean is, when we transform it into the spherical coordinates, what will be our E total? E total will be, it will be v by 2 pi whole cube and 4 pi 0 to kf, and inside what you will have h cross square, but k to the power of 4 now, divide by 2m then dk. This will be the case, and we can integrate it, and we can evaluate this integral. This is v by 2 pi whole cube, this is 4 pi, keep it out, okay, h bar square out, divided by 2m out. You integrate it, you will get k to the power of 5, divide by 5, 0 to kf. That will be the case. So what will be the total energy? So E total will be V by 2 pi square 3 pi square n by V whole raised power 5 by 3. And no, it's not going to be like this. I am doing it wrong. So here you will have V by 2 pi square, and then you will have some cancellations, and these cancellations will lead to h bar square, because 4 and 2 and these terms will cut down, and you will have 2m here, and finally here you will have kf raised power 5 divided by 5. So this will be our E total. Now substituting kf, now if we substitute kf in this equation, what will be Et? That will be v by 2 pi square, and then you will have h bar square by 2m, then you will have 3 pi square n by v whole raised power 5 by 3, and times 1 by 5. So we have used the value of kf that was calculated already, okay, and we had calculated the value of kf as 3 pi square n by v whole raised power 1 by 3. So this is what we have used, and we have obtained the total energy. Now if we simplify down this all, and we come up with the dependence, and what's that dependence? That dependence is this E total. The total energy of this fermionic non-interacting gas comes out to be 3 by 5 NEF, where this EF is our Fermi energy. So what we have done here is we have used second quantization. We have derived the total energy of non-interacting Fermi gas at absolute zero temperature, and the result is 3 by 5 NEF. And this is what reflects the distribution of fermions in energy states up to the Fermi level. So suppose this is the Fermi level, okay, up to this Fermi energy, with the total energy being proportional to this Fermi energy and the number of the particles in the system. So this total energy is proportional to the number of the particles in the system, and it's proportional to this Fermi Fermi energy. Now, this problem certainly demonstrates the power of second quantization in handling these many-body systems, and the Pauli's exclusion principle in principle for fermions. So, with this, I would like to say goodbye.